For over a century, general relativity has modeled the universe as a smooth, continuous fabric. Space and time warp and curve together, allowing us to predict large-scale phenomena like planetary orbits and gravity with near-perfect accuracy. But when we look at the subatomic scale, that smooth fabric disappears. The quantum realm is defined by discrete, granular events. Particles snap into position, and energy is exchanged in indivisible packets called quanta. The mathematics used to describe these two realities cannot communicate. One side relies on analog, continuous space. The other requires a digital, quantized framework. Because equations break down when trying to apply the rules of one to the other, physicists typically treat the macro and micro realities as two distinct and separate domains. Bridging the gap between the continuous and the quantized is the central challenge of theoretical physics. The Oscillatory Dynamics Transductive Bridging Theorem, or ODTBT, offers a solution to this tension. Its core premise is that continuity and quantization are not opposing forces. Instead, they are alternating phases of the same system. Rather than treating these as conflicting physical structures, the theory posits a single universal oscillation governing the transitions between continuous waves and discrete particles across all scales. We can now look at the specific mathematical mechanism ODTBT proposes, the geometric structure that allows physical reality to transition between analog and digital states. Recognizing this dynamic transductive bridge allows the fragmented landscape of modern physics to be modeled as a single system. ODTBT builds its foundation on basic trigonometric functions rather than relying on the discovery of a new particle type. This image shows the standard sine and cosine formulas for periodic motion. Here, the cosine function represents expression, the outward continuous flow matching the smooth mechanics of classical physics. The sine function represents compression, a return toward equilibrium, defining a discrete, quantized event. Applying this trigonometric duality alters how we define fundamental physical properties. Under this model, standard quantities like mass and energy are no longer treated as static numerical values. Looking at this text, we see the mathematical representation of scalar energy oscillating between continuous and discrete phases over time. The equation separates energy into E0 for the discrete state and E1 for the continuous state, showing that energy constantly cycles between the two. This cycle of expression and compression operates constantly across all scales of matter. When an observer takes a measurement, they capture a specific moment in time. This creates the appearance of a permanently fixed state, even though the system remains intrinsically dynamic. Redefining physical properties as dynamic vibrating fields provides a pathway for resolving the quantum classical paradox. We can apply this sine-cosine duality model directly to the phenomenon of wave-particle duality. This is the time-dependent Schrödinger equation, the standard physics baseline for measuring and predicting a quantum state. ODTBT reinterprets this mathematical probability wave as a physical oscillation, where matter transitions between a continuous wave state and a discrete particle state. The framework identifies the specific mechanism executing this transition as the twist. It acts as the transductive bridge between domains. The center intersection of this geometric figure 8 acts as the 0 point. This is the exact location where continuous potential converges and transforms into discrete reality. Moving up from subatomic particles, this structure also maps onto the macroscopic fabric of spacetime. The theorem presents a structural model where time operates in discrete, quantized steps, while physical space remains a continuous medium. This document shows the required mathematical differentiation. Time steps are expressed using the discrete Kronecker delta function, while continuous space is mapped using the Dirac delta function. The transductive twist harmonizes these regimes, weaving digital time and analog space into unified spacetime. The twist functions as the geometric engine required to drive spacetime forward, constantly transforming potential states into manifested physical forms. Quantum entanglement serves as a critical stress test of the ODTBT framework. Under the standard Copenhagen interpretation, physicists struggle to explain nonlocality, the fact that separated particles seem to communicate instantly without a physical link. This equation is the ODTBT mathematical model for a two-particle entangled state. According to the theorem, these particles do not send signals to each other across a void. Instead, they exist within a shared, self-sustaining oscillatory loop managed by the twist. This text shows how a quantum collapse functions. The twist maintains a transductive bridge between possibilities. When an observation disrupts the sine wave equilibrium, it forces the system out of superposition, locking in a discrete state for both entangled particles. This approach shares historical roots with the work of David Bohm and his deterministic pilot wave theory. This is Bohm's formula for particle motion. It uses a pilot wave to guide a particle along a defined path, providing a mathematical precedent for non-random quantum mechanics. Bohm argued for a hidden implicate order of unbroken wholeness, which maps to ODTBT's continuous field. In turn, his explicate order represents the discrete physical particles we actually measure. Within this framework, entanglement is localized within a continuous wave structure, hidden entirely beneath discrete observation. ODTBT takes these mechanics and scales them from the subatomic realm to the macroscopic world. Because the foundational math relies on endlessly scalable trigonometric functions, the oscillatory process applies universally. The author proposes mapping this oscillatory model onto complex biological systems, describing molecular transcription as cycles between continuous information potential and discrete functional outcomes. Moving up to cosmology, the theorem frames gravitational waves as macroscopic transductive cycles, shifting the vacuum of space between continuous and discrete phases. The theory suggests structural uniformity. Biology, gravity, and quantum mechanics could all be governed by the exact same transductive engine. ODTBT replaces the necessity for inherent, unpredictable randomness with a self-regulating deterministic transductive process. It provides a mechanism where the smooth fabric of relativity and the granular packets of quantum mechanics are simply different phases of a single cycle. We started with an unresolved paradox between Einstein's smooth universe and Heisenberg's granular one. Resolving this historic gap may not require the discovery of a new unifying particle, but rather a shift in our ontological framework. Reconciling the universe requires recognizing that the continuous continuum and the discrete quanta are just two alternating swings of the same pendulum.